Hello there. Snow day today, so I am going to implement the optimizer. Yeah, that shouldn't take too long. It's pretty simple, hopefully, but then we will have um a trainable neural network, and then after that, I'll have to figure out how to actually like implement this, like integrate this into Tinygrad. We can figure that out later. I think here, let me, here, standard grading sets. So, params I equals params I minus, um, learning rate times gradients. Okay, so, yeah, std dot v. So, module std, um, you know, I think, okay, so in this function, it takes in like multiple nodes here. Main, we, that's main here. So if we look at where we actually use this, backward here, I think if we the LSP CLD, amazing. Okay, auto autograd dot cpp backward. Okay, we don't call gradient descent over here. Um, wait, I have no idea how this code works. Okay, so now I understand. This loops through all of the inputs and calculates the gradients. And then the optimizer. Then we have the optimizer do the thing. Optimizer. Okay. Optimizer. Dot step. What does this mean? I am. Oh, I do not know C++ syntax. Um, params. So is params. Yeah, params. Okay, so yeah, we defined those earlier. Wait a second. Over here, we define this as standard vec as like standard library vector, but in over here we take in a custom list of holy vibe code. Um, uh, I mean, I think it's pretty okay. So really, sorry, let me move this stuff over here. Shit. Um, Now, here. So, what the, amazing. Okay. So, in our version, C++ version, all of the parameters are like a struct that has its value and its gradient. So the way we do backpropagation is that in the C++ version, we go through and like calculate all the gradients and update this variable right here. And then when we optimize, we just like take the value and modify it based on the gradients. But in Verilog, like in our Verilog version, we don't really have that sort of state. So I'm just trying to, because our actual parameters, maybe it would help if I actually knew how the how a backwards pass code worked. Let me close this. Uh, there. Backward. .v. Okay. So, um, let's just go through this and figure out what's up. So, this is number of neurons. This is number of layers. Our inputs are the activations, the weights, and dl over dy. So the gradient of loss with respect to the outputs. Um, how is this? That's odd. Dude. How is this run in the bench? Um, backward. Okay, so there's n equals to m equals to network inputs x vals, w vals, b vals, network outputs. Cool. Target for loss computation equals 2 times y dl over dy equals 2 times y minus targets for MSE. Does that make sense? So MSE of y hats equal to um y minus y hat squared. So then when you differentiate this, dl over dy equals product rule. So product rule? power rule, you bring this is now 2 times y minus y hat. That checks out. So then we have our backward outputs. So what we're trying to find is dl over dw and dl over db, where weight, and this is the bias. Cool. So now okay, we run the forward pass and we store the intermediate states. Then we run the backwards pass and yeah. So we need we need to feed in the weight values because unlike the bias, because the bias is addition, the gradients with respect to the bias is just the gradient with respect to the output. Um, I think it's like uh, so Z is equal to X times W plus B. Change in Z with respect to change in B. So for this is constant, and then we're asking if I change like B by some minuscule amount, how much does Z change? Well, it changes by that same minuscule amount because it's just addition. So for that, it's 1. That's the gradient. But for um, change in Z with respect to the change in weights, or I guess like with respect to the change in inputs, because that tells you how much you need to back. Well, um, it would be, I think it's the wait. Uh, okay, so then over here, display weight grad, display vice grad, forward pass. Okay, yeah, we can make test backward, make file. Let's um ah cd dot dots. Holy moly! What? Um, syntax error. TB adder. TB network. Okay, it's probably something. Oh, errors in port declaration. Line 13 is syntax error. Odd. Continue. Uh, syntax errors, TV backward, getting errors when running test backward. Ah, okay, because we had the unfinished unfinished file. Okay, here. Okay, so in the forward pass inputs 2, 1, output 3.6, 1.97, target 0.5, 1. Then we have our intermediate activations and um powered off my headphones. Here. So what we want is DLDW and DLDB. DLDW. Um, um, okay, so our weights gradients are grouped by layer. So um, delta, I guess D L D W like 0 and then D L, etc. So if we want to optimize these weights, well, it's actually It's actually pretty simple. We just have to make sure we index correctly. What did I? Okay. Let me close this and work on sgd.b. No, reload. Okay. Input wire clock. Do we really need a clock? I don't think so. So input wire. I guess we should have our parameters first. Hashtag parameter n equals 4, parameter m equals 4, close parenthesis, input wire signs w, so be m times n times n, close parentheses times 16 minus 1 to 0, put the w on one side of that. W and input wire signs m times, wait, so 1 m times n times 16 minus 1. We don't need this parenthesis. Minus 1 to 0 b, because 1 bias per neuron per layer. Then input wire signs here, so m times n times n times 16 minus 1. Do I have an extra parenthesis? Here. Minus 1, 0, dl, dw, and then finally input wire signs m times n times 16. I think it'd be cleaner. On the other one, we do n times m times 16. So we should probably keep it consistent. N times m minus 1, 0, dl, db. And then output wire signed. So it'll just be, let me w new and output wire signed new. Okay. I think that's it. I don't think we need like a start wire or clock wire or anything, because it's just multiplication and addition. There's no iteration we need. Really none of that. Yeah. Okay, so um politics you I remember there being like 4 loops, combinational logic, Verilog. Combinational for loop. Here, Okay, this is not very helpful. Um, U, okay, P, huh. You go back URL, G, G, L, L. Okay, your chip verified. Interesting. Well, I mean, maybe it'd be helpful first to figure out what exactly we want our circuit to look like. So, the way I think would make most sense is we have a module that does SGD for a single um for a single parameter, so like a single weight and a single DW and just returns W new. I guess to make it more general, I don't know, P like parameter, and then we just replicate that. We just have like, like a crap ton of these circuits, all reading from a specific uh, points in each sort of matrix, and then each writing to a specific point in the outputs. So I think we could do that with just a gen bar. So I think later we had a gen bar here. Generate block. Gen bar I, and yeah, I think that's fine. Um, the only thing is like we have weights and biases. So I think it might make sense to literally just before running this, like pretty much just concatenating weights, bias, and then also concatenating um DL DW with DL DB. Think these should be like that because it's partial. Nobody cares though. And then we don't have to worry about like swapping between. We can just iterate iterate through. That is a poor use of two arrows. And then we could also have like concatenated weight new, B new, and then um, before returning, we just assign W new to this portion of what we have and B new to this portion. So let's do that, I suppose. I forget how you concatenate. Uh, did we do this in like neuron? Um, Here, you. Concatenate numbers in Verilog. Holy smokes, that is a lot. Okay, 1-bit wire, 2-bit wire to store A and B. Um, right, braces. Okay, so assign here wire wire. So it'd be um this, and then we need another parenthesis here plus this. Actually, I think we can factor out the 16 here. So now we have this times 16, and then m times um. So this side, let's not overcomplicate it. It does not really matter. 0 params assign params equals WB, and then we want another params new, and then gradients. Um, Assign gradients equals, so that'd be DL, DW, DLB, and because all these are the same size, this will work. Okay, so now we can here back to our generate block. Generate for I equals 0, I is less than um m times, so w is equal to I guess num is equal to m times n times n. B num is equal to just m times n. So w num plus b num is equal to m times n times uh m times n squared plus m times n. So this right here is equal to this is not productive use of our time. We can just copy this and delete these 16s. There. I equals I plus 1. Begin. So we want to um I guess you should also take a learning rate. Input wire signed. So that is literally just 16-bit number R. Yay. So assign params new I equals params I minus LR times gradients I. I have a feeling something is gonna get messed up. This doesn't feel like correct Verilog. Um, then uh, and then we can assign W new params new equals params new ah oh I just realized this will not work because all of that is multiplied by 16. We'll just like uh so it has to be I times 16 or uh when I is 0 it would be I plus 1 times 16 and then minus 1 to I times 16 and then it should be the same for all of the others in terms of indexing. Here, here, delete this, paste this, delete this, paste this. Magnificent. Um, so this is equal to this. Um, trying to do the parentheses matching in my head. Here, ah, hmm. So that'd be until this. What? 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 Semicolon. Forgot the semicolon here. Here, assign b new equals params new. What? Minus 1 to 0. So now This should be good. Um, let's make a test bench for this, I suppose. Test slash tb std.b. So let's just make up some stuff because I don't really want to, instantiate the network, do the forward pass, then do the backward pass, then do the SGD. We can just make up, okay, let's say um, n is equal to 1, m is equal to 2. So the weights are W0, W1. Simplicity, let's just have them be 0.7. We can just have them both in 1 actually. 1, 1. Bias is equal to B0, B1. That can also be 1, 1. Weight, bias, and then actually no, screw it. Let's just do the forward pass, whatever. Yeah. So TB backward. We should just be able to copy most of this and then also instantiate the and then run SGD. Here, vterm, tmux, quad, continue. Okay, I've implemented sgd.b. I've copied tb backward to tb sgd.b. Can you complete its can you complete that file so that it also tests SGD? I'm gonna go get some water. Overwrite SGD.b. Why? Huh. Um, yeah. Why are you completely replacing the logic? Was there something wrong with the way in which we were concatenating previously? Your new code is much more. Your new code is much more verbose. stay hydrated. Um, that makes sense. That I do not understand that. No content. Do not know if that's good or bad. Oh, I suppose it's good because it is now completing the test bench. Yeah, this was actually a lot easier than I thought it'd be. Sure, bro. Let us regenerate it. Regenerator. Forward pass. Cool. Okay. I was planning on just like stopping once the optimizer test was complete, but I sort of want to like implement, I don't know, a toy network just with everything we built. That'd be fun. Ooh. Um, make test SGD. Holy smokes, that is a lot of outputs. Let's go through this SGD optimizer test. Learning rate 0.0977. I assume that's floating point error. Um, we should definitely refactor this to use higher precision because this is sort of painful. Forward pass 4 SGD 2 1 output 3 blah blah blah. Okay, this is our MSE. Output pass gradients computed. Okay, it doesn't tell us the gradients, but that's fine. How do I? Okay, W nu equals W minus LR times blah blah. So these are our new weights. This is for layer 1, this is for layer 2, guess layer 0 and layer 1, and then updated biases. So the forward pass, we overfit. Yes, amazing. Okay. Now let's make like um a tiny network. So tb XOR.b. Actually, I don't really want to do this now. Let me. I feel like I haven't committed. Can you check the git status and then commits? Make multiple commits if necessary and push to dev. And that's good. Um, add backward pass module. This is a terrible, terrible commit message. Commit message be one sentence most. Don't enumerate literally everything. If they want to know how something happens, they can read the code. They can read the diff. Add backwards from finishing. Add SGD optimize module and test. Push git push origin dev. Cool. Amazing. Actually, you know what? I am going to implement XOR as like a demonstration. So that way I can like have a little demo video of like this is my framework thing running the XOR problem, and then it's like uh I forget what I was going to say. Cool. Let us tbsgd.b. Okay. So what shall our architecture be? I think we need at least 2 layers for XOR. So yeah, 2 layers. Inputs come in, and then you know, you know how a neural network works. Or if you don't, well, uh, I'm not sure. Uh, so yeah, this is m equals to n equals to. Yeah, one thing I want to add like support for next time is non-homogeneous numbers neurons. So if I want to have like you know this, like who are you to stop me? Right now, a lot of our logic, like our indexing, depends on the fact that all the layers are uniform. But I'm sure we can figure that out. Module TB SGD local param n equals n. Sorry, look. Um, 2 local param m equals 2. Actually, we can just copy this. Okay, then um here. Yeah, we need 2 inputs and 1 output. Uh, right, because it's like 1 0 it's 1, or we can just have 1 1 be the equivalent of 1 and 0 0 be the equivalent of 0. Yeah. Actually, you know what? Let's hey Cloud. Um. How much work would it be to refactor this so that we can have non-homogeneous neuron counts in layers, e.g. Um, 2 inputs to 3 neurons, 1 output. Right now, it looks a lot of our indexing logic depends on this homogen, but it's also but it is quite restricted to these kinds of problems which this can solve. E.g., XOR requires 2 inputs, 1 output. Maybe I should have ultra thinked there, or ultra thunk. Yeah, I don't know. Feel like we should probably abstract away a lot of the indexing. We might have, I feel like we probably have a bunch of like redundancy. That was a really passive sentence. I feel like we probably have. We have much redundancy. Um, okay, every indexing formula assumes n by n weight matrices. Parameter arrays. Two to 3 hours of focused work. Never trust God. Here, let's see. Um, um, yes, um, sketch out the interface. There's no way it's going to take 2 to 3 hours to focus work. Well, I hope. Sauteed. Interesting. Yeah. Yes. Um, okay. Let's actually read what it said. Uh, here is a sketch for supporting variable layer sizes. Instead of nm, use number of weight layers, not counting inputs. Layer sizes, including inputs. Derived constants. Input size 0, output size. Okay, that makes sense. Pre-computed offsets. Layer I has layer sizes I plus 1 times layer sizes. This doesn't actually seem like that this doesn't seem that difficult to implement. Function automatic integer. Is this synthesizable? Thought like functions were not synthesizable. Okay, how do network V, okay, yeah, yeah, start implementing the, how would we do this in, like, a synthesizable way, though? That is the question which I am asking. I'm going to parameter arrays. Are those functions synthesizable? How would, if not, would we refactor them to be, or I guess rethink them to redesign? Let me see if I have any email. Um, Google launches personal intelligence, turning Gemini into a proactive AI assistant. Mega IPO. Oh, um, what's a VH file? Um, yep. Oh, here. Um, all checks pass. Sounds great. Can we abstract? Can we like I don't know abstract away the indexing from the individual away from the individual modules to another module which they um, synthesize slash import or whatever. IDK, we're implementing this for all of these themes. Actually, yeah, let's implement layer Duffy. Layer v2. V. Don't put it to a new file. We have get a reason. Here. That looks good. Why is this taking so long? Odd. Ooh. Um. Terminated. Um. Okay. What did I do? I just hit two. Um. Two. Okay. Yes. Refactor network copy. Do you want to overwrite? Sure, bro. Uh. Wait a second. Wait. Did you just hard code bunch of numbers, bro? Okay, let me actually read the code it wrote this time because I no longer trust it. Okay, let's head up to the top. Um, copy input to intermediate states. Cool. Var. So for s equals 1, s is okay. S equals, that makes sense. Assign layer start. S equals layer done. S minus 1. Okay, that makes sense. Output done. Network done. Um, okay. Genvar I um for I equals 1. Okay, that looks good to me. Um, here. Holy smokes. Are you still hard coding stuff, man? Just we should be able to create a network with an arbitrary number of layers, an arbitrary number of nodes. Obviously, some practical limits like 16-bit cap and overflow, whatever. But you get what I mean. Yeah. Okay. Um, the end goal is that 12 be a Tinygrad backend. So the Tinygrad code be compiled into this HDL. So can't you just have them take in these sizes as parameters and divide the parameters in the test bench? Um, yes. Yes. Okay. Amazing. Then once this is done, we can run the XOR. After this, I think to be honest, I don't know that much about Tinygrad. I just thought it was cool name. I have no idea how you'd integrate this, but we can figure that out. Here. Yeah, this still looks really weird to me. Uh, what the hell? Oh, there. Conversation compacted. E. Holy smokes. commit and push dev. Make commit sentence commit one sentence only explains why and why we made these changes. Somebody wishes to know what changed or how we changed it, they can look at the diff. Here, implement add TV XOR. One. Okay. 0 0 0 0 1 2 2. Okay. 0 layer 1 layer 2. Local h equals okay. Here. XOR true table. Weights. Special spices. Okay, so 100 picks. Okay. Make test XOR. Huh. That's odd. Ah, back backwards pass doesn't have to be working because the gradients are all zero. Ah, why is accepted? It's odd. Holy smokes. Um, ah, okay. So I figured it out. We were dropping the sign before. That was bad. Uh, um, Um, Amazing. Didn't push it down. Okay, amazing. Cool. I guess like before I leave, yeah, goodbye.